So yes, we stopped last week here with the micas, and I have uploaded this class on Moodle, so you can download it, yes, and then you can also see the single tetrahedrons. So, and we stopped then last week with this figure that was this one. I can also upload this PowerPoint then on Moodle, then you have these figures as well. Yep. So yes, we stopped with this one. That was one of our last figures last week, and that is actually the arrangement of the tetrahedrons and the metals in the mineral talc. Yeah? And the talc is a sheet silicate, I told you this, and this talc has here in the interlayer, there is no atom. Yeah? So, and then I showed you this other figure. So that it was this one here, we have also a sheet silicate, but here we have in the interlayer, we will have some atoms, and this atom is called the potassium, or it is a potassium. So, and if we are talking about these sheet silicates, then we have a TOT structure. TOT, TOT. What means TOT? That means just tetrahedron, octahedron, tetrahedron. And then we can make a sketch map, and this sketch map looks like this. So then we have here one tetrahedron, we have the octahedron, then we have the next tetrahedron, and then we have here the interlayer, and we are continuing here with the next tetrahedron, octahedron, and here I don't like to paint it by now because we cannot clean it or clear it from the wall, yeah? So that is the TOT structure, and last week we stopped with this, here with the formulas for the talc and for the biotite. I introduced here the 3 octahedral micas, these are the biotites, and the d-octahedral micas, and these are the micas. So, and these d-octahedral micas are called the d-octahedral micas because there is one octahedral space empty, yes, and that was this one. So now Neil I told Neil he should go with you through all these silicate structures again in the practical. This you will now do in the next practical because a mistake happens. So and could you find out the mistake while you are studying this? A big pity that happens to me. So, if you are doing here the electron balance, here you have the magnesium, you have 2 electrons in the outermost ring, then you have here 3 magnesiums, you have 6 magnesiums, and then you have 6 magnesiums, and then you have to balance this. Then we have here too much silica inside. Yes, I have written here Si8, and that is wrong. So please correct this now in your notice. Yeah. So Neil will also tell it you again, and I will do it also on Moodle for those of you who are not today in the class. So and therefore we don't need now 8 silicas, we need 4. Yes, then it is correct. So and then there is another big mistake there. Because I forgot, I don't know why I forgot this, yeah. So, I forgot to put the oxygen there, yes? Here you have oxygen, here you have oxygen, 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 oxygen. Then we have here oxygen, 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 oxygen. And here we have the OH2. Now it is correct. OH2. Then we have here the OH2. So you have always to check carefully what I'm telling you in class, yeah? Because most of the time it is wrong. So then we have to balance now it. You know that the oxygen has two spaces, yeah, that is -2, and here we can now add the positive charge one, then we have here 2, 4, 6. So and then the silica has +4, yes, then 4 are multiplied by 4, that is then 16 plus this 6, then we have 22. So and then we have to balance it, and here we have 1 oxygen here. So and then we need here 10 oxygen. So then we have 10 multiplied by -2 is 20, and then you have here 1 O here inside, and then you have the 22. So and now we have also to correct here, because here we put then here 1 potassium inside, and then we have 1 atom here, 1 electron in excess, that is an electron. So and then we are putting here on the tetrahedron side 1 silica out, and putting then 1 aluminium inside, and then the whole thing is solved. And then there should here not be 7, it should be here 3. So and here it should be 2, yes, because here we made the Cermak exchange from there. Then we have here 2 aluminium, and I told you last week, yes, we can replace the silica with aluminium, because the aluminium is a little bit bigger like the silica, and we can replace the aluminium also with the magnesium, and that is then our magnesium Cermak. That was this one here, yeah. And if we are doing the same game with calcium, then we have a calcium Cermak, and in some other minerals we are doing it with iron, and then we have the iron Cermak. So and then that must here be Si2, and here it must be the Si3, and here it must be Si4, and here it must be Si3, and here it must be Si2. So and now it's complete, and now it's correct, yeah? Yes, make a picture, yes, and delete the picture from last week because that was wrong. So, and tell me when you are done, yeah, with writing it in your notebook, because then I will clean it up, and then we will continue with the antipodes. And the antipodes say F and the 8 silica, yeah? So if you are writing down at home before you go to bed these structures, yeah, that's always a good exercise before going to sleep, yeah? Then just write it down in such a way. Start always here with this thing. For the sheet silicate, you have your M2 space, the M1, the interlayer, then you have your tetrahedron, they make just a T, and then you have only to have in mind that you have these micas have always 10 oxygen, yeah? The feldspar has 8 oxygen, then the olivines have 4 oxygen, the pyroxenes has 6 oxygen, and the garnets has 12 oxygen. So that you must have in mind. So and then the mica, that is a hydrous mineral, then just you can put automatically the OH2 groups. If we are talking about kaolinite or some other clay minerals, then you have more than you have maybe OH4, yes? And if we are talking about the serpentines, we have also OH4. But here in class, we are doing just the mineral chemistry from the most common rock form in minerals that you have then on ground to, where you can play around with. Yeah? That's the only thing what we are doing, we are playing around. So, and these then are the sheet silicates. And there I have another figure. You will get these figures also later on more and more and more. So that is this one, just to repeat the whole thing, I will then also upload it. You have here this ionosilicates. Yes, we have already done it. These are the olivine and the garnets and the alumosilicates. These are just isolated single tetrahedrons. Yeah, we have done this in class. Then we have the sorosilicates. These are this one. These are just two tetrahedrons which are connected to each other. Then we have the cyclosilicates. These are just tetrahedrons which are connected to a ring or a cycle, and I showed you in class the picture from the mineral beryl. Yeah, there you can see that this beryllium crystal was very nicely formed and shaped according to the arrangement of these tetrahedrons here. So then we have the tectosilicates. We have also done it by now. Quartz is the most famous and the most common one. That is where all the corners of the tetrahedrons connected with each other. So, but also the feldspars. Then we have the nepheline. That is a silica undersaturated mineral. We will maybe talk about the nephelines and the calcite and the analcime later. Yeah. So, and then we have here the phyllosilicates, yeah, and the phyllosilicates I just showed you by now. These are the micas. Yeah, here we have the mica, another phyllosilicate, that is the chloride, the serpentine, the talc, the pyrophyllite, and the clay. So, and now we will continue with the double chain silicates. These are the amphiboles. We have already done the single chain silicates, and the single chain silicates, these are the pyroxenes, and I gave you last week the most six important end members of the pyroxenes. Yeah, we had there the autopyroxene, and we had the clinopyroxenes, and the autopyroxene, that was the enstatite and the ferrocylite, and the clinopyroxenes, that has been the dioxide, the Heidelbergite, the charlite, and the aquite. Yep, here I have something more to the micas, I mean to the phyllosilicates. So here you have your talc structure, yeah? That is this one with the empty space here, yeah? That is by now clear. So and if you are talking about the mica structure with the TOT, interlayer TOT structure, then we have this one here, and these are the biotides, and the potassium is just sitting here right in the interlayer, yeah? So that is the TOT structure with the interlayer, and here we have the TOT structure like you can see it in the talc, or like it is here in the phyllite, yeah? Then we have here just the empty space, and when you are writing it down to train yourself, then just use this for making an empty space. And here at the deoctahedral micas, you have here the empty space on the M1 side, whereas here at the trioctahedral micas, it is filled up. So if we are talking about the serpentine, and in the next week I will, or maybe in 2 weeks, I will also introduce the serpentine, then the serpentine, here the modification antigorite, has only a TO structure. And if we are talking about the mineral brucite, then we have only the octahedral structure, because the brucite does not contain silica. Yeah? That is just MgOH2. So that's so far to this. So and now we are continuing with the double chain silicates. So we have done the pyroxenes, and now we are ending up our mineral chemistry with the double chain silicates. And here you can't see anymore the tetrahedrons, but you know by now how such a double chain silicate looks like. Then we can clean this. So in the double chain silicates, these are the amphiboles. So, and there we have also autoamphiboles. I made here just a shortcut for amphiboles, and we have here clinoamphiboles. So and now these amphiboles, they are more complex, that means they have more end members, and I will just give you here the most important end members. So here the amphiboles they have, and that is written wrong, that is auto, yes. So all the amphiboles have these are also hydrous minerals, and then we can make here an OH2 group. So and then all the amphiboles they have also oxygen, and they have 22 oxygen. So and then they have also tetrahedrons, and then they have also M spaces. And they have also an interlayer. So and now we have 5 M spaces. We are starting here with the smallest one. They have 2 and 1 spaces. Then they have an M2 and M3. 2 and 2. 2 and 5. And 2 and 3. So that's the right thing. So they have all in all, they have 7 M spaces. So when they have 8 octaeder spaces, all of them have O22 and they have an OH2. So and if we are talking about autoamphiboles, if you are going back to your pyroxenes, yes, just checking your pyroxenes. That is here not M5, that is M4. So if you are going back to your pyroxenes and checking the autopyroxenes, then you can figure out that these pyroxenes, there you have then the magnesium end member and the iron end member, yes? So and if you are, and I mean a pyroxene, that is a chain silicate, and amphiboles are double chain silicates. So and now we are, then you have to remember how many silica can be on the tetrahedron side, and this is in an autoamphibole, that is 8 silica. So and this silica can then be substituted by aluminium, yeah? So but now we are dealing with autoamphiboles, then you have 8 silicas, O22, OH2. So and then if you are checking your if you are checking your manuscript with the pyroxenes, so then we are starting here with the first amphibole, and that is the anthophyllite. So that is the antophyllite, and the antophyllite is orthorhombic. So and now we have to make the antophyllite, and the antophyllite is the magnesium-rich end member. Then you are putting here just the magnesium, 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 yeah? So in the M1 spaces are the smaller spaces, and the M4 spaces are the biggest spaces, yeah? They are becoming always towards to the front bigger, yeah? So in the interlayer space here, that is a really big one. So and now we have constructed our amphibole, and we have here 7 magnesium, that is 7 multiplied by 2 is 14. Then we have 8 silica, 8 silica multiplied by 4, what is this? 4 multiplied by 8, that is 32. And then we have 32 plus 14 here, yeah? 32 plus 14, that is then all in all 46. 46, and then we have here 46 multiplied by minus, this 22 multiplied by minus 2, that is 44, and then we have here this 2 oxygen, and then it's balanced 46. Do you agree with me? So and now we have constructed constructed the antophyllite. So and now we are constructing another guy which is called the cummingtonite. So and that can be remembered very easily, coming tonight, yeah? Coming tonight. So if we are making a coming tonight, then we are making a mixture of 2 end members. Yeah, that can also be recorded very easily, a mixture of 2 end members. Yeah. Yes. So coming tonight is a mixture of 2 end members. So what can we mix up while we are talking about autoamphiboles? We can only mix up 2 end members with atoms of nearly the same size. So then we will just go, that is the first end member, and here we are going to the next end member, that is the grunerite. So grunerite plus antophyllite, that makes then the cummingtonite. So and now we are making which exchange we can make here with the antophyllite. That is the FM exchange, it's always the FM, yeah? So and that means we are now exchanging the magnesium with the iron, yeah? So and then, you know, iron, the size of the bubble and the weight of the iron bubble is nearly the same as the one from the magnesium. So and then we have just exchanged this with iron, and then we have still the Si8, yeah, the silica, the O22, OH2. So and now we are making from grunerite and antophyllite, we are making the cummingtonite, and then you just feel free how many grunerite is or how many antophyllite is in the grunerite. So and then you can just make an exchange, a mixture of both, yeah. So, but there could be here also 5 magnesium or 6 iron or so, yeah. The cummingtonite is just a mixture of the antophyllite and the grunerite, and then we have Si8, O22, OH2. So, and these are now our autoamphiboles, yeah. So in these autoamphiboles, they have under the microscope, we will do this then later, they have a straight distinction, yeah. So that means when they become dark under cross nickels, then it is parallel to the north-south axis or east-west axis under the microscope. So now we are continuing here with the Kleiner amphiboles, and I will give you the most important ones. So, and in some literature, the interlayer here in the amphiboles is also written as the A space, yeah? So, and now we are continuing here with one of the very famous Kleiner amphiboles, that is the tremolite. So, how can you remember the tremolite? We have here also Si8, O22, OH2. So if you are hydrating a dioxide, you know by now what a dioxide is. That is a Kleiner pyroxene, and the chemical formula of this dioxide is CaMgSi2O6. So, and now you are a gardener, yes, and then you have here a lot of dioxide on the ground, and you are running around and watering this dioxide, and maybe you are doing this for the next 50,000 years. Then you will make from your dioxide an hydrous mineral, and this hydrous mineral is then called the tremolite. Yeah? These are always the bridges which you should have in mind or not. We will do this later when we are writing down mineral reaction, and we will also show you in the lab again and again and again how to write down such mineral reactions. So, but anyway, from a dioxide we can make a tremolite, and that means this tremolite must contain calcium and magnesium. Yeah? So, and now which bubble is the bigger one, the calcium or the magnesium? Calcium, yes. So, and I told you that how here in front the M4 spaces are the biggest octahedral spaces in such an amphibole, yeah, in the amphibole structure. So, and therefore we have to put here we have once more our A space, yes, or make it so, yeah. Then we have here 2 calcium, because these are the bigger bubbles. Then we are putting it here on the bigger spaces. Then there is the tremolite, Ca2Mg5, Si8, O22, OH2, and that is now the tremolite. Yeah. So, and here on the M1 spaces you can then put the aluminium. Yeah, if you like to build up another amphibole. Yeah. So there are thousands of amphiboles around, but I will show you only the most important ones. So, and now we are making the next a good friend of the actinolite, of the tremolite, that is the actinolite. So, and then you have also calcium in front. Then we are putting here 2 magnesium, but then we are making an Fn exchange, and then we have a mixture of magnesium and iron, yeah? And then we have the actinolite. So, but you can put here also only 1 iron or 2 iron and more magnesium, but this is then just the Fn exchange, and then it's the same as here. We are just writing here Fn, and then you know we have just made an iron-magnesium exchange. So, and as I told you also last week, the magnesium-rich minerals are formed at higher temperatures, whereas the iron-rich minerals are formed at lower temperatures. Yeah. So, and that is then just the Fn. So, but now we are making a very famous amphibole, yeah? That is the Hornblende, yeah? That's a German name. So the mineralogist who found the Hornblende was a German. So, then we can write down here again O22, OH2. So, but now the Hornblende does not have we are putting now here in front a sodium, yeah? Then we have here 2 calcium. So, and then if we are putting here a sodium, then we are making here, then we have to balance it here with an aluminium. That means here we have the Si7. Yes. And then we have here again Mg, and then we make here again an Mg, and here Fe, and here Fe. This is the Hornblende, yeah? So, but additionally to the Hornblende, I'm writing now down another Hornblende. Then you have here again the sodium, the calcium, the magnesium again. So, and then we are making a Charmak exchange. Then we are putting here an aluminium. Then we have here Al2, Si6, O22, OH2. So, and here we are writing that just down the Ts, and that is for the Charmak exchange. So, if you are increasing the pressure, then this mineral is making a Charmak exchange, because then the volume for one atomic cell becomes smaller and the density will increase, and then you have to replace some bubbles with smaller bubbles, and the aluminium is smaller than the iron and the magnesium, yeah? That is then the pressure effect, yeah? So, but now we are going to the next amphibole. Yes, now we are making a Glaucophan. So, and the Glaucophan is a typical mineral in blue schists. So, and that is the reason why the blue schists are blue, and that is because of the amphibole Glaucophan, and the Glaucophan is a blue mineral. So, what's so funny here? So, and the Glaucophan has the 2 sodium. So, because we can also put here on our A space a sodium, but we can also put on the M4 space a sodium, yeah? So, and then the Glaucophan has here on one M4 space a magnesium. Then here on these 2 spaces are aluminium, and then we have here 3 spaces left, and we make here a magnesium, and here we can make iron, and here we have iron 2+, and here we have iron 3+. So, and then we have here Si8, O22, OH2. So that means the sodium is even a bigger bubble as the calcium. Yes, it's bigger than the calcium, but has only 1 electron in the outermost string, and then you have to balance this to the back. Yeah? So, and you can balance this either with aluminium or with iron 3+. So then make here just a bracket, and it's just to show you how to replace the different things. So now we are coming to the next one, that is the powder side. And the powder side has only one sodium, that is here on the A space. Then you have here calcium, 2 calcium on the M4 spaces. So, and then you have here then four magnesium. Then we have our 4 magnesium. Then you are putting here an aluminium. Then you have here 1 aluminium on the octahedral side, 1 aluminium on the tetrahedral side, Si7. The whole thing is of course 8, yeah? You can always write it down behind the bracket. O22, OH2. So then you have the edenite. So and the edenite has then also the sodium here, then 2 calcium here. Then you have 5 Mg. And then you have here Al, Si7, O8, O22, OH2. So that means if we are comparing the edenite with the powder side, then the powder side is doing additionally a Czarmak substitution. So and last not least, we have here the Rebecite. So and the Rebecite has then also, it has 2 sodium here, 1 calcium. So and then you have here again the Fm exchange. So in this Fm exchange you can have here, it depends on the balance, a mixture of Fe2 plus and Fe3 plus. So and then here again, there is no substitution, you are just balancing it here on the M spaces. You have here your Si8, O22, OH2. Yep. So, and these are only some amphiboles. I mean, there are a few hundreds more, but I gave you just this one, that is enough for you. So, at the amphiboles, as you can see here, you have much more varieties or possibilities to exchange or substitute the different things, or the different atoms, or a combination of them, yeah? But the exchange factors, that is then always the Fm exchange, it is very important. Then you have all 3 Czarmak exchanges, the magnesium Czarmak, the iron Czarmak, and the calcium Czarmak. And you have this replacement. If you are putting a potassium, a sodium, like it is here, with 1 electron in the outermost rim, you can make the charge balance here on the tetrahedron side, or as it's shown here, with iron 2 plus and iron 3 plus, yeah? So, and that is the only thing what you should know about the amphiboles, yeah? I mean about the silicate structures of the amphiboles. And now we are through with the most important silicate structures or those which I have given to you that we can play around with. That means that we can make, then we can formulate some mineral reactions or chemical reactions. That is totally easy by now, and you should by now also know how the crystallographic system influences the external structure of such a mineral. Yeah, I showed you at the first class last week how the external structures influences the internal structure and vice versa. Yeah, that we have done by now. So, and I advise you to study this because there I will have a few questions at the examination and in the test which we are writing on the beach. Yes, we are now in the planning stage for the Corvo Island field trip, yeah? So now we have done this, we have done the sheet silicates, so we have done mineral structures, yes, this we have also done, we have done the, how is it called, the plagioclases and the K-feldspar, yeah? These are the ones with the Si8. So now we are talking about mafic minerals, and we are talking about felsic minerals. Yeah, that is the next thing. So mafic minerals are mainly minerals which occur in mafic rocks. So in the mafic rock, for example, that is a rock from the oceanic crust. Yeah. For example, the gabbro, and you saw it at the ES106 field trip. You saw the gabbros, yeah. At Yamuna Creek, or how is it called? Yamuna Creek, yeah. There you saw the gabbros, and the gabbros is a typical rock formed at the oceanic crust, and it is a mafic rock, and it is a mafic rock because it is silica undersaturated, yeah. So these mafic rocks, usually they can contain a little bit quartz, but usually not, yeah. And this gabbro, which you saw in the ES106 field trip, is a quartz-free mafic rock. So and that means there's less than 58% SiO2 inside. So and therefore in such a mafic rock you will find mafic minerals, and mafic minerals are dark minerals, yeah? So in one dark mineral, these are the phyllosilicates, that means the sheet silicates. These are the micas, and they are mafic minerals. And the most common mica, that is the biotite, that is the dark mica, yes, that is the trioctaedral mica, yeah? So in this trioctaedral mica, here you have again a summary from the mineral chemical formula, yeah? So, and we did all the 4 end members last week and today because I told you that what I told you last week about the silica inside the mafic minerals was wrong, but now you should got it right. So, and then we have the muscovite, and that is the white mica, and I showed you this white mica, these are the p-octaedral mica, and they do not contain magnesium and iron, they contain instead of magnesium and iron aluminium, and that makes them silver shiny, yeah? So, by now you should recognize that all these mafic minerals, they contain magnesium and iron, yeah? That makes them dark. So, and if, or I will give you in 2 or 3 weeks, we will start to do also microscopic work. So, and then you will get thin section, and then you, before you put the thin section on the microscope or under the microscope, then you can just check it with the naked eye if there are some dark minerals inside, or if there are mainly dark minerals, yeah, then you know immediately this rock is mafic rock, yeah. Now it's closed, and you just bring one of the Schwarz collection. So, and then another mafic minerals, these are the inosilicates, and here we have the double chain silicate, and the double chain silicate I have just written here on the board, and here this, or I brought you the example from the Hornblende. Yes, we have sodium, calcium, iron, magnesium, so and that makes this amphibolt dark, yeah, and all the amphibolts are dark. I mean this actinolite, for example, where I put it here, no, not the actinolite, is coming tonight, no, not, or the grunolite, they are greenish, because if the mafic minerals are formed under lower temperature, then they are greenish. If they are formed under higher temperatures and pressures, then they are becoming more black. So, and that is the same for the biotite. The biotite, which is formed at lower temperature, is greenish because of the iron. Yes, you can see this then under the microscope. And if the biotite was formed at higher temperatures, then it is more brownish. It becomes then more dark, yeah? So, and if the biotite is more brownish, then you know this biotite was formed at higher temperatures, and this biotite contains then more magnesium, yeah? So, and if the biotite contains more magnesium, then the biotite contains also more fluorine, yeah? We will discuss this later. So, and then other inosilicates, these are the single chain silicates, I told you this by now as well, and these are the pyroxenes. So these are our main minerals. Yes, that is fine. Just to show it to them. So, and if you can then bring also a fancy one. So then we have here some that is a gabo, yes. And if you are just checking this gabo and then just give it through, if you are just checking this gabo, then you can make by now, only from this 2 weeks class, you can say, or you can tell me now a lot, yeah? You have mainly dark minerals inside, yeah? You have mainly dark minerals inside, and if you have mainly dark minerals inside, then this is a mafic rock. And then you can tell me by just looking at it, then you know which minerals are the dark minerals, yeah? Use then the hand lens, and later on the microscope, yeah? Yes, wait, now we have everything, it's just to make the contrast. So, and then you have the dark minerals, and then you, by studying these dark minerals, you can tell me if these are pyroxenes, if these are biotites, or if these are amphibolites, yeah? So, and then you can just write down the chemistries from these minerals which you can obtain here in the rock, and then you have done actually a lot. So then we are going here now to the next page. So, and here we have then the inosilicates, as I told you, the pyroxenes. So, and we have the nesosilicates inside, these are the olivines. So, and the olivine is a green mineral. Can you see in this hand specimen a green mineral? No. So that means that this is an gabo and this is intermediate. Do we have some orchite crystals here? So, because here in this inosilicates, there is one pyroxene, it is called an orchite, and during our excursion in Koro, you will find a lot of orchites, yeah? So, and Neil is just bringing for us some orchites. So, because these pyroxenes, they are blackish, and the amphibolites are also very dark, yeah? So, and now you should be able to find out in the hand specimen if this is a pyroxene or an amphibolite. So, and therefore you are looking for the symmetry. That is the pyroxene. I make just PYX, and here you have the amph. So, in the pyroxene has if you are making a head cut, yes. So, if you are checking this one, so, and you guys can check this one. So, and you guys can check this one. So, and if you are looking at these black minerals inside, that is an orchite andesite, and these orchite andesites you can find here in Vitilegu, you can find them on Vanuatu, and these black crystals are orchites, and the orchite has cleavage. We will also check it while we are doing microscopic work then, but just for now, roughly. So the orchite has a cleavage from 89 degrees to 91. So that means nearly 90 by 90, yeah? So, and that is this angle here. Yes, then you have here nearly the 90 degree. Or here from the cleavage, all these angles, they are nearly 90 degree, yeah? So, and if you are watching now the orchite just with the naked eye, then you can find some crystals. It depends how they are located in the basalt, yeah? So, but if it is the head cut, then you can find this cleavage of 90 degree. So, whereas the amphiboles, they are totally different. So, the amphiboles have 124 to 56. So then we have here the 124, and here we have the 56, and these are also all the angles here inside from the cleavage, yeah? So that is then the head cut of an amphibole, 124 to 56, and the pyroxenes have 89 to 91, or roughly 90, yeah? So, and that is the way how you can identify in the hand specimen if it is an orchite andesite, for example, or a hornblende andesite, for example, yeah? So, but we will train this during our field trip, and now it starts to rain. So, and if you have greenish minerals inside, that is the olivine. Do we have somewhere samples of dunite or hartspurite? So these are then the mafic minerals from our collection, and now we are going to the felsic minerals. But let us at first wait for Neil that you have also seen the olivine. So in olivine nodules you will also find a lot of them during our field trip, yeah? So these olivine nodules, they are xenoliths which occur at Moro Island in the basalt. Yeah? They just when the basaltic belt or the andesitic belt erupts to the Earth's surface, then they will sample everything what is lying around, you know, in 90 kilometer step or something like this. And if there is a dunite or a hartspurite or a nersolite on the way, then the smelt will just pick it up and bring it to the Earth's surface. Yeah? These are the xenolites. But we have also olivine-bearing basalt, so that means the olivine is then a mineral in these basalts. Maybe we have here one. No, but here, for example, we have something else, and here we take inside, yeah, here. Here within this biotite you have a dunite. Here these green minerals, yeah, these are the olivines, yeah. Just check it and give it around. And here I have something else. I just found it by accident. These are greenish amphiboles, yeah. And these greenish amphiboles, they are forming such needles, yeah. And these greenish amphiboles are very, I found one, are very common for these autoamphiboles, yeah. So, and here the greenish mineral, that is the olivine, yeah. And the olivine, the typical metal olivine, is has a forsterite component of 90 and 3000 ppm nickel. So and now these are mafic minerals. Now we are going to the felsic minerals, and we have also done the felsic minerals. These, for example, the tectosilicates, and there we have discussed the feldspars. Yeah. So we have the alkali feldspars. You know, these are the one, the potassium-bearing feldspars. That is the autocline, the sanidine, and the microcline. And here you have the chemical formula. So in the microcline is the low temperature variation, whereas the sanidine, that is the high temperature variation, and the autoclass is medium. So and then you have in these feldspars also the albite, and the albite that is also a plagioclase, and that is as a sodium. And then of course you have the solid solution of autoclass and albite. Yeah, I showed you this last week by using the triangle. Yeah, but you will see this triangle again. So and then we have the plagioclases. We have the anortite. Yeah, that is the calcium plagioclase. Then we have again the albite. You know, if you remember the triangle. Then we have the sodium plagioclase, and then we have the plagioclase solid solution of anortite and albite. Yeah, that was on the borderline on the ground of the triangle, and there you have a complete solid solution. But if we are talking about the alkali feldspars, then we have only a solid solution above 750 degrees Celsius, because we know, I showed you this also, there is a immiscibility gap. So and then a very common tectosilicate, that is the quartz, yeah, SiO2. Then we have the feldspar-2-ides, that is the nepheline and the leucite. That means this nepheline and this leucite is also occurs only in silicate undersaturated rocks. And you can also find some nepheline and leucites here in Vanua on Viti-Levu. So and the nepheline, that is then just is hexagonal, and that is just albite minus 2 quartz. When we are talking next semester in the volcanology class, then we will take care about this, about silica saturated melts and about silica undersaturated melts. And the leucite is actually doing the same as the nepheline, but it is tetragonal, and it is just if you are subtracting from an autoclass quartz. So that means if you have a silica undersaturated melt, yeah, a silica undersaturated melt, then you will form, instead of albite, you will form a nepheline, and instead of K-feldspar, you will form a leucite. Because there is not enough silica in the melt. Or you have removed a lot of silica before, yeah? The melt is cooling down, and then after you have formed an albite, and after you have formed an autoclass, you will then form a nepheline and the leucite, and they are called then the feldspar-2-ides. So that we don't need it is just the book which I used to get all these infos. So, but now we are starting with the classification of the igneous rock. So in the classification we have here a texture, and that is a coarse-grained rock which has no preferred orientation, and we are talking here about a plutonic igneous rock. So and then we have in this plutonic igneous rock, we have some dark minerals inside, and these are mafic minerals in the QAPF. I will show you then also the QAPF. So then we have these pinkish minerals inside, that is the alkali feldspar. It is a felsic mineral. We have here the silver shiny mineral inside, that is this one here, that is the quartz. And here we have this white mineral inside, that is the plagioclase. So in this rock is called the granite. So this rock is called the granite. And then you can just have a hand specimen here from the granite, and you can have a hand specimen here from the granite. And here you can have another hand specimen. you can have another one. So, and then you can see, you can find easily the dark mineral inside, yeah? That is the what? That is the biotite. And you can find the pinkish mineral inside, that is the alkali feldspar, and you can find silver, shiny, glassy mineral inside, that is then the quartz, and you can find this white mineral inside, that is the plagioclase, yeah? So, and here that is now the method to classify certain rocks. We are using therefore triangles, yeah? So, and in the next few weeks you will see a lot of triangles and used in a different way. So in petrology we are always classifying the things, and we are always using ratios. We are using ratios of certain components in certain minerals. So to make a very easy classification, we are using the triangles because then we can describe three components in space. So, and then we have here an XYZ triangle. So, and here at this corner we have 100% of component X. Here at this corner we have 100% of component Y. And at this corner we have 100% of component Z. So, and if we are going, if we are sitting here somewhere, then we have 33% of component X, 33% of component Z, and 33% of component Y. So, and these ratios changing always here in the triangle, but if we are adding all the three ratios from the three component X, Y, Z, then we have always to get at the end 100% or 1. Yeah? I mean 1 if we are just using from 0 to 1. So, and if we are now using two triangles, one triangle is here at the top, so and here one triangle is here below, then we are getting the QAPF diagram. So the QAPF diagram can be used to classify inchless rocks. So in there we have two QAPF diagrams, one for the plutonic inchless rocks and one for the volcanic inchless rocks. So and here this triangle here in pinkish or light brownish, these are the silica saturated inchless rocks, and here one to the bottom, the light blue colored one, that is for the silica undersaturated plutonic inchless rocks. So and then we have here QAPF, Q that stands for quartz, yeah. And if we have a rock with this composition here, then we have a rock which contains 200% of quartz, yeah. Then we have here the letter A, and A that is then for the alkali feldspars, that means for the K feldspars. Here we have P, that is for the plagioclases, and here to the top bottom we have the feldspar to these are the silica undersaturated rocks. So that means from here to here you will not find any quartz, yeah? And from here to here you will not find any feldspar to yeah? Otherwise, if you find this, something is completely wrong. So, and then we have here the different inchless plutonic rocks. Here in this field we have the rock called granite, yeah? That is the one which I just gave you around. So, in the granite contains the quartz, it contains here alkali feldspar, and it contains plagioclases, yeah? So then we have here the granodiorite. The granodiorite is a little bit more fine grained compared to the granite, and it contains more plagioclase. So and here we have the tonalite, and the tonalite contains much more plagioclase. So and if you remember our field trip to at the Yamuna Creek, you find not only gabbros, you find also a lot of tonalites, yeah? And this tonalite had black minerals inside. The black mineral was a biotite. Then you have quartz inside, but you could not find any or very rare pinkish mineral inside because the tonalite has just much more plagioclase. Yeah, you remember this. We have a tonalite here. So, and then here on this side, you have then a very pinkish look, and that is the alkali feldspar granite. Yeah. So here to the bottom, we are getting more or we have less and less silica inside. We have quartz cyanide, quartz monzonite, quartz monzodiorite, and these monzonites and monzodiorites, you saw them at the Sambeco River. So, and then here we are running nearly out of silica. We have cyanide, monzonite, and monzodiorite. And here we have an anorthosite, and you saw also some anorthosites at the Sambeco River, and that is a rock which contains nearly or only plagioclases. So, and if you are going here below, then we have the silica undersaturated rocks. That means you have then no quartz anymore, and you have then this feldspar wheats, the nepheline, and the leucite. So now let us just for need, and I can show you the tonalite just to remember how these tonalites look like. These tonalites which we will bring, these are tonalites which we also saw the same one at Yahuna Creek. So hopefully today. So now I have here other two rocks. Here we have the famous tonalite from Yahuna Creek. So if you are watching it, then you can see easily that there is no K-feldspar inside, yeah, because that's the field where the tonalite is at home in the QAPF triangle, yeah. So the rock is too big for the. Here we go. So that is the tonalite. So and now the tonalite has also a lot of quartz inside. So but now we are going down here to the diorite. Here we have diorite, Gabriel. Here is the diorite somewhere around, yeah. And then you can see that this diorite contains much more mafic minerals, yeah. And less silica, yeah, because we are running just somewhere around here, yeah. So here for you as well. Nobody should die without having seen a diorite before. So, and what do we have here? Here we have the monzonite, yeah. So in the monzonite we are sitting then here. Yes, and here you have the dunite here, the greenish one. So here we have now the monzonite. The monzonite, yeah. This monzonite, and here is the Yes, yes, but these are the sunglasses for the boys, because these are the dark ones. So, this is now the classification plot, yeah, for the plutonic rocks, yeah, plutonic igneous rock, but every plutonic rock is an igneous rock. So, and now we will show what I have prepared next for a figure, yes. Here we have again a triangle, and this triangle is used for classifying the gabbros, yeah. So, and here we have 100% plagioclase, here we have 100% olivine, here we have 100% pyroxene. So on this side we have the gabbro, yeah. And I showed you by now the gabbro, yeah, and the gabbro has then a lot of pyroxenes inside and plagioclases, yeah. Pyroxene, that is the black mineral, the plagioclase is the white mineral. So, and this is then here the gabbros. So, and here on the bottom we have the plagioclase bearing ultramafic rocks, yeah. We will discuss that also, the ultramafic rocks in detail. These are the metal rocks, and you will see a lot of them during our field trip in Coro, yeah. And we are planning to sample tons of them. So, and here on the opposite side you have the troctolite. And the troctolite has then instead of pyroxenes, olivine. So and here in the middle we have the olivine gabbros, yeah? The olivine gabbros is just a very silica undersaturated gabbro, and this gabbro has the olivines. So this gabbro which I just showed to you now, that is an olivine, has no olivines, and then this gabbro is floating somewhere here on the line. So and here on the top we have the anorthosites, and the anorthosites, these are this anorthite plagioclase bearing rock, and these rocks contain more than 90% anorthite, yeah? So in these anorthite bearing rocks, they are always formed at the top of a magma chamber. So why is it formed at the top of the magma chamber? That is because the anorthite plagioclase has a very low density, yeah? So and if a mineral has a very low density, then it's floating up to the top of the magma chamber, yeah? So whereas olivine and orgite, for example, they will sink to the bottom of a magma chamber because they have a higher density, yeah? We will discuss this then also later. And then we have some minerals they are floating in the magma chamber, and that is because they have the same density as the surrounding melt. Yeah? So, and here we have now the next one, we have the classification of the peridotites. So, and the peridotites, these are all these mantle rocks. Yeah? So this one which you are holding here, everybody has seen it by now here, these olivines, yeah? So an olivine makes up 67% of the Earth's mantle is made up of olivine, yeah? So and if we have only olivines, yeah, then we have a rock which is called a dunite, yeah? So if this olivine occurs together with autopyroxenes here, which you will also see during our field trip, then we are talking about an Harzburgite, yeah? I will also show you some of these nodules tomorrow, yeah, because I have a lot of Harzburgites and dersolites in my office. So, and if we have here then also some clinopyroxenes inside, then we are talking about a mersonite, yeah? Yes, here we have a dunite, yeah, wonderful what we have here. So this is then a dunite, and you can see there's just only olivine inside, yeah? So if we have then a little bit autopyroxene inside, then we are talking about an Harzburgite. If we have clinopyroxenes as well inside, then we are talking about a mersonite. So in these dunite, Harzburgite and mersonite, they are formed in different levels in the subcontinental mantle, for example, yeah? And all these dunites, Harzburgites and dersolites, they are always, they are residual rocks from a melt. So you have originally a melt, for example, you have a theoretical mantle composition that is the pyrodite. If this pyrodite rises up, then you are forming a melt, then you are forming a basaltic rock somewhere at the oceanic crust, and you have the residuum. So in the residuum of this, these are then here the dersolites, the Harzburgites, or the dunites. I will show it to you some diagrams about this later. So from here to here we are forming peridotites. That means the group of dersolites, Harzburgites, and dunites, they are called peridotites. So, and if we are going down below 40 or more than 40%, if you have more than 40% clinopyroxenes and autopyroxenes inside, that means your rock contains the less and less olivine, then you are forming here rocks which are called pyroxenites, and you have here the websterites and the olivine websterites. In these websterites here on the bottom, you do not have any olivine inside, or only in very, very minor concentrations. Yeah? So that is the relationship of our ultramafic rocks. So we had the classification of the phaneritic Inchnet rocks, that was the QAPF. Then we have the classification of the gabbroid rocks. The gabbroid rocks, these are these rocks formed at the top of the oceanic crust, yeah, the first 3 kilometers. So, and then we have the mantle rocks, and these are the peridotites and the pyroxenites. These are then the ultramafic rocks. So now we will show what we have now. Now we have the nomenclature of the volcanic rocks. So, and the volcanic rocks can also be described in the QAPF diagram, but the volcanic rocks look completely different from the plutonic rocks. Here, for example, we have the rhyolite. Yeah? The rhyolite. The rhyolite. Here again, a rhyolite. And one for you. and one for you. So if you are watching these rhyolites, then you can see very easily that they are looking completely different from that granite here. Yeah, I will not give you the granites now again around because you just saw it. So they are looking completely different because this granite is coarse grained, the rhyolite is fine grained, the rhyolite is fine grained because it is an extrusiva, and the granite is an intrusiva, and then if you have an intrusiva, this melt has much more time to cool down compared to a melt from an extrusiva, which will be cooled down immediately from the seawater, or a rhyolite immediately from the air. Yeah? So, but if you are checking this chemical, the composition of this rhyolite, then the chemistry is the same as the one before from the granite. Let us just go to the front. So here we have the chemical composition, the relationship between quartz, plagioclase, and alkali feldspar. Then we are forming here in this field the granite. Yeah. So now we are going back to the QAPF from the extrusivas. Then we have here the rhyolite. Yeah. So the melt, which was from which this rhyolite was formed, has the same chemistry as the one who was responsible to form the granite. Yeah? It is just the other is an extrusiva and the other an intrusiva. Yeah? So, and therefore here we have in this field, when we are forming this stud is formed from the same melt, for example, as the granodiorite. Yeah? So, and therefore every extrusiva has an equivalent rock from the chemistry from the intrusivas. Yeah, it's just the type of emplacement. Yeah, the intrusiva becoming somewhere stuck in the Earth's crust, cooling down very slowly, whereas the intrusiva are just erupting. Yeah. So, and here we have the phonolite. Yeah, that is the silica undersaturated intrusiva, and these phonolites are called phonolites because they used it in former time as a music instrument. Yeah. So the others they have used the biotides for the sunglasses, and others have used the biotides for the sunglasses and used plates from these phonolites. Yeah, and if you have very thin plates, and then you can use it as a bell, yeah, ding dong. Therefore, they are called phonolites. Yeah. So, and here we have now another classification diagram, yeah, for igneous rocks. So, and here on the x-axis, we have the silica concentration. Yeah, you can powder such a rock. Yeah, you can powder them, and then you are bringing it in some molten glasses. So, and then you get such a glass plate where you have the powder inside from your crushed rocks, and then you can use XRF, and then you can measure the mineral chemistry, and then you know how many weight percent of SiO2 is inside, and blah 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 from all the oxide elements. And here we have on the x-axis we have the SiO2 concentration, and on the y-axis we have the alkalis, and here we have sodium oxide and potassium oxide. So, and in this diagram, sodium oxide and potassium oxide is added and plotted against the silica concentration. So, and on this side, here from, let us say, 35% to 45 weight percent, we are talking about ultra basic rocks. Yeah, I mean, some authors writing or saying ultra basic, others, as myself, we are saying ultra mafic. But mafic and basic is the same, yeah? So only that you get not confused, it is the same. So, and if you have silica concentrations lower than 45 weight%, then we are talking about ultramafic or ultra-basic rocks. Yeah? So, and now we have here the basic or the mafic rocks. It is between a silica concentration of 45 to about 52%, and these are the mafic or basic rocks. And what is now a mafic or a basic rock? You saw just one today. These are the gabros, yeah. A gabbro is a basic or a mafic rock, and here it is written basalt, and the basalt is written because it is for the extrusivas, yeah. So the basalt has the same chemical composition as a gabbro, yeah. But the gabbro is an intrusiva and the basalt is an extrusiva. So then we have here between 53 and 62%, we have the intermediate rocks. That means we have here the andesites, yeah. And you saw during our field trip, you saw a lot of andesites, yeah. They are very common here, and here in Fiji you have potassium-rich andesites, yeah. So in these andesites you find here two types. You find the plagioclase-bearing andesites, then you have large white needles inside, and that works in following way, because I told you the plagioclase, especially the anorthite, has a lower density as the surrounding melt. Then it will be swimming or floating at the top of the magma chamber. Then another melt, the andesitic melt, comes from below and is just picking up these plagioclases. Yeah? So, and therefore the matrix of these andesites, which you saw in the field, is very fine-grained, but the plagioclase needles are very big compared to the fine-grained matrix. Yeah? So, and that is because the petrogenesis from these plagioclases has nothing to do with the petrogenesis of the andesitic melt. They were just picked up on the way. So, and the same is for this orchite. You saw also some other andesites, and these were the orchite-bearing andesites, and these orchites, they are sinking down at the ground of the magma chamber and were then picked up by another andesitic melt, or by a melt of a totally different composition which has mixed up from this residual melt in this magma chamber where the plagioclases were separated from the orchite. So, and therefore we have then here above 77 weight%, here on this side we have the whitelites. Yeah? These are then silica saturated inchness or silica saturated volcanic rocks or extrusivas. Yeah? So these are these diagrams. So, and if we are talking about inchness rocks, then we have also the tuff. Yeah? We have the tuff, we have the lapilli stones, we have the lapilli tuff, and we have the breccias. And during our field trip, you saw also some tuffs, and you saw also the mudstones. Yeah? So, and this tuff is then created if you have a volcanic eruption which is very gas rich. Yeah? They are very fast, this gas is moving very, or the ash flows. Yeah? And from this ash flow, you can create these tuffs. And you have the different types of tuff. You have the lithic tuff, the crystal tuff, and the vitric tuff. And here you have some rock fragments inside. Yeah? These rock fragments has nothing to do with the ash flow. It was just picked up. Yeah? So, and then we have here where you have some crystals inside. So, and here you have some glass inside. So, and if you are going to this side, then you have here tuff, which is ash smaller than 2 millimeters. Then we have the lapilli, and that is 2 to 64 millimeters. And the lapillis are actually only very small balls. Yeah? So, and these lapillis are formed during the eruption, and these are formed when you have a phreatomagmatic eruption. Do you remember what a phreatomagmatic eruption is? I don't know if I have done it in ES 106, but I think so. So, but anyway, if you are talking about phreatomagmatic eruptions, That is an eruption like it was in 1980 at Mount St. Helens. So, and why was the eruption of Mount St. Helens so dangerous? One thing is Americans are very fat and then they could not flew so fast, yeah. Yes, that is one thing. The other thing is Mount St. Helens was covered because now the volcano or the mountain is much more smaller because most of the upper parts of the volcano flew apart while the eruption took place. So the dangerous thing was Mount St. Helens was under an ice cap. So and what or snow cap, yeah. So and what happens if the whole hot melt comes in contact with this ice cap? So the ice will melt very fast. So and if the ice melts very fast and heat is heated up by a melt which is maybe 700 or 800 or even more 1000 degree hot, then you will produce very fast what? Steam. So and if you have producing from ice immediately steam, then you have a huge volume extraction, yeah? So and this volume extraction that took place there while Mount St. Helens was then blasted or become blasted away, and therefore it was so explosive. So if the melt comes in contact with water, then we are forming lapilli stones or lapilli tuff. So these lapillis are the small roundish balls, and they are forming, or it is a typical sign for a phreatomagmatic eruption. So and because they are only formed in this scenario. So I don't know if we can find here some lapillis, do we? But not on, I don't think so that we can find them on Koro. But anyway, we will then find some lapillis next semester because I'm telling next semester actually the same as this semester. So, and then we have here blocks and bombs, yeah? And blocks and bombs, these are bigger than 64 millimeters in diameter. They can be of this size, yeah? So, and if you are walking around, you know, on the crater on an erupting volcano, I have done this in the past, and then you have not to watch on the ground, because normally as a geologist you have always to walk around like this, because you are looking on the ground what type of rocks you can find, yeah? So, but if you are at an active volcano, then you have to walk around like this, because the rocks and the bombs, they are coming from above. So, and these are then the pyroclastic breccias and agglomerates, and I thought you saw also some on the ES-106 filter, yeah? That was in this mud flow. And yes, and you will see them also on Koro, yeah. I remember. So, and here we have then the rock types, you know, that is just the introduction to the whole thing what we are doing here. This is an erupting volcano, and I can show you then also pictures which I made in South Italy, because there I have visited Etna while it was erupting, and there I was dancing on the crater. And this looks like, no, that is probably not Etna, that is Stromboli. So Stromboli is one of the volcanic islands in the Mediterranean Sea in Italy. And Stromboli is erupting every 20 minutes. So, and that is actually a very reliable good volcano, because you don't like to visit a volcano and then it is not erupting, yeah? So, but Stromboli is erupting every 20 minutes, and I will show you then the figures or pictures. I made a lot of pictures. And you can, at Stromboli, you can just go to the neighbor crater, yeah? So, and then you can go there during the night, because during the night it looks then very spectacular, yeah? So anyway, and this is how it looks like there, and then the pieces are falling away or falling down, yeah. So, but if we are now going again away from our volcanic eruption, yeah, where we can see something is going on, some new material is formed. If we are checking the micro textures, then this is the or macro textures. This is the macro texture from such a granite. Yeah, you have a coarse grained rock, and you can see this in the hand space event because you can identify every mineral with the naked eye. Yeah. So if you are checking a basalt, you have also some basalts here. Then the macro textures look completely different from the macro textures from a granite, yeah? Because here, at the first thing, you can identify nothing, is it? Because it is very fine grained, and that is because it was cooled down very fast. So even if you are using a hand lens and checking this basalt, that is for you very homogeneous, yeah, and for me as well, yeah. So and if you are checking this, in here you have the macro textures. The next thing is you are checking the micro textures, yeah. And the micro textures you are checking with a microscope, yeah. So, but anyway, then you can see here from this granite you can still see the minerals. Here, this mineral, for example, these needles here, that is the mineral plagioclase. Yeah, they are forming always these twins. You will see them also then under the microscope. So, and here you have the K-feldspar, for example, and here, for example, you have something else. Yeah. But anyway, you have the macro textures, you have the micro textures. And if we are talking about plutonic rocks, then it is much more easier to identify all the minerals, even in macro textures. So then we have the different rock types. We have igneous rocks, yeah. These are there we subdivide in the extrusivas, these are the volcanics. From the intrusivas, these are the plutonics. So then we have the sedimentary rocks. These are the clastic, the detritic sediments, the chemical sediments, and the biogenic sediments. And we discussed this also in the ES 106. And next semester, LNOR will offer the course about sedimentary geology or sediments, and that is the ES 201, yeah? And there she will go more in detail with sedimentary rocks and the foraminifers and all these things. So, and I will offer next semester additionally the volcanic class, that is hot melts and humans or something like this. And there we will discuss more in detail the igneous rocks, yeah, the chemistry. I mean not only these Larifari diagrams, which I showed you before, real diagrams. So in this semester, in this class, we will discuss or talk then more about metamorphic rocks, because there is no special class of metamorphic rocks. So, and therefore we will talk about the protolites. The protolite, that is the precursor, and the protolite for a metamorphic rock can be an igneous rock, or can be a sedimentary rock, or can also be another metamorphic rock. So, and if we are talking about metamorphic rocks, then we have orogenic metamorphic rocks. These are metamorphic rocks related to subduction or to collision. And then we have oceanic metamorphic rocks, and these are rocks related to contact metamorphic events. So, having all these rocks, we are talking about the rock cycle. So, and the rock cycle is also a part of this class when you are checking the course outline. So in the rock cycle, here at the top, we have the magma, yeah? So when this magma can be produced, and all the first rocks on this planet, yeah, these were inchless rocks. Yeah? So and these inchless rocks were produced by volcanic eruption or by the emplacement of magma somewhere in the Earth's mantle. Yeah? So and if we are switching off the light, maybe the quality is here better. Not really. So and then we have cooling and solidification of this magma. So then we are forming here an solid inchless rock. Yeah? So in this solid inchless rock, we can do two things with it. We can, if we have this solid inchless rock somewhere on the continental crust, or we must not always talk about continental crust, we have it just somewhere, for example, in the Yamanua Creek. Yeah? So when these inchless rocks, these solid inchless rocks, becoming then weathered, and then they becoming these particles become then transported away and become somewhere deposited. Yeah. So then we are forming. We have at first weathering and alteration, and we are forming then from these particles, from these alterated and weathered particles from our inchless rock, we are forming then a sediment. Yeah. Or we have here our solidified inchless rock, and we are sending it down via subduction zone or via continent-continent collision zone. Then we will increase the heat and the pressure. Yes, we are going then this way, and then we are forming from our inchless rock a metamorphic rock. Yeah. So if we have now here our metamorphic rock, then we can send them down to hell, for example, and then our metamorphic rock becomes molten again, yeah? And if it becomes molten again, then we are forming again melt, and that will end up in the volcanic eruption or in the formation of some granitoids, that means some plutonic rocks, yeah? Then we are forming from this metamorphic rocks again an inchless rock. But we can also leave the inchless rock like here, and then we are starting to weathering and transport and deposit our formerly metamorphic rock. Then we will again form a sediment. Yeah. So, but we can then from here to here, cementation takes place, and then we are forming here. We have a sediment. Here we are forming then the sedimentary rock. We can heat up and we can put heat on pressure on this sedimentary rock, and then we are forming here again a metamorphic rock. Yeah? So, and that is the rock cycle. So, and the rock cycle goes always together with the Wilson cycle. The Wilson cycle is a periodical event which takes an average every 450 million years place, and that is when all the landmass going together, and after they went together, yes, then we are forming a supercontinent, yeah? So we have always the formation of supercontinents, and we have the breakup of supercontinents. So, and if all the landmass is together, then we have a supercontinent, and afterwards the breakup takes place of the supercontinent, then all the continents are apart from each other, like the situation is nowadays, yeah? So, and therefore, when the continents are falling apart from each other, then we are forming always new material. So, and this new material is formed at the middle oceanic ridges, yeah? Because that is the driving engine to put the plates apart from each other, yeah? So, and if the plates are apart from each other, then it becomes always more hot on this planet, yeah? So, because that is the upwelling of the oceanic crust. So, and then we are heating up the seawater, and that is also, it is actually the main reason why we have here a rise up of the seawater, yeah? Because we have now also the planetary climate change. So, and if you are going to Vanuatu, yeah, and for those who have done the field trip to Vanuatu, you saw everywhere these hot springs, yeah. That is the heating up of the water, And you saw also at Savu Savu everywhere where the seawater was whistling, yeah? And that is just released from CO2 and methane into the atmosphere. So, and for those who are doing the ES3 over next semester, they will see this next semester. And then you can just come on the field trip with maybe 20 eggs, and then you can boil the eggs in these hot springs, yeah? People are doing this there. So then we have here the sedimentary rocks, and that is just a summary. Sedimentary rocks are products of weathering. Yeah, we have mechanical and chemical destruction of rocks. So chemical destruction of rocks, I told you this last week, that is, we are removing some elements. For example, we are removing from the K-feldspar the potassium by weathering. So then the K-feldspar is falling in pieces, and that is chemical weathering, because we are making then from our K-feldspar, we are making then carbonate, that is a clay. So mechanical weathering, that is just if you are going there and hammering it, yeah? So then we have B transport, that is mechanical movement of rock fragments, detritus, yeah, these are this detrital material, and dissolved components by flowing water, and that is gravity driven. Of course, the water is always flowing down from the hill into the ocean, in not vice versa. So then in the ocean floor, for example, we have the deposition of detritus in low energy environments. Low energy environments means such as the deep sea basins, yeah, there is no water flux or water flow, so that you can transport these certain particles at the continental shelf platforms, in lakes, in braided river systems, and the chemical precipitation of minerals from oversaturated solutions like the calcite, the gypsum, and the halite, that is then by evaporation. Yes, we did this all in the ES106. I will just refresh some things. So then we have the lithification, that is the diagenesis, that is then the reduction of the pore space. Yeah, I showed you also this in the PowerPoints from the sedimentary rocks last semester. You can just watch them again. I think everybody have it. Then, of course, we are changing the formation of the water content. We have transformation of carbonate into mud to limestone, or of clay mud into argillitic sedimentary rocks. Okay, then we are stopping here.
If you have the rock stand,
yes, just bring it back, yeah.